Thank you. Good evening to all of you. It is my honor to introduce Yves Prairie. As Claire said, is a professor for more than 30 years at the Quebec University in Montreal. He is also UNESCO chair in environmental chair. And is an aquatic biogeochemistry expert, and he research on the biochemistry of carbon in aquatic ecosystems, and especially in lakes and reservoirs. More specifically, he analyzes the factors that will define the dynamics of gases in lakes and reservoirs, and build models that will make it possible to quantify and predict greenhouse gas emission. And it is to work on such models that Yves has decided to come 6 months in Lyon. For 6 months in Lyon. So his work has an international scope. He's enriched the biochemistry of carbon and aquatic systems. And in addition to these contributions, significant contributions to knowledge and to the academic world, the Yves research and his skills and competence have been acknowledged as sources of a common interest, because he's an expert in the IPCC working group on inundated lands, and is one of the key authors of Chapter 7 of the revision 2019 of the directives of the IPCC for national inventory of GHG greenhouse gas. So a brief introduction, and you will understand more in the presentation. So in addition to his work as researcher, he is an amazing teacher, and he's also very generous, and he puts his knowledge to the younger generations of researchers. So I want to thank Yves for his presence in Lyon and for his advice. And it is a great opportunity and a chance to welcome him, for us to welcome him in Lyon. And please do not hesitate to contact him, because I'm sure he will be happy to provide his knowledge. And thank you to UHR Auto Lyon. And have a great webinar. Thank you, Fanny. Thank you to Claire-Lise for the kind introduction. And welcome to all of you. Thank you for... Okay, let me put my screen on. And a special thanks to H2O'Lyon, which has facilitated my visit in Lyon for the access to my visit in Lyon for next month. So it is a great pleasure for me to share with you what I do, which I've been doing for quite a while now. Now, do you all see my screen? I suppose so. So I will talk about the emissions of greenhouse gas, GHG, from large dams, and establish the cross the border between fundamental and applied. So how fundamental can feed the applied. Now, large dams are nothing new in this domain. As you know, this is the global map of the largest dams in the 6,800 red dots, which correspond to all the dams listed in the world, and the total volume is in excess of 100,000 cubic meter or kilometer of water, and the surface total water is about 350,000 square kilometer, and this amounts for 10% of the total land water, that is lakes and ponds. So it's quite a significant quantity. And this is the current situation. We know that there are also dams that will be built in the world. Thousands, all the dams will not be built, let's face it. Some of them were just like under study, but those in blue have already been constructed, and new dams will be built elsewhere in the world, but especially, as you can see, mainly in China, in India, and of course, Middle East and Europe. and of course, lots in South America. New dams are planned in North America, but it's a lower number. Now, dams, contribute to the greenhouse gas emission. This is not new either. And in fact, this year we're celebrating the 30 years of the first publication by John Rudd in Canada, who asked himself the question now, do reservoirs are reservoirs are a significant source of greenhouse gas? And you see you see here only a few of the articles published on this topic. So it's not new, this issue. And I've decided that, well, in my presentation today, in there will be 4 sections. Why do reservoirs produce greenhouse gas and why do we pay attention to it? I'll be brief. What is the scope of the phenomenon at the global scale, world scale? What is the impact on our climate of the greenhouse gases on the climate? Because, emission is one thing, but the climatic impact on the climate is another one. And finally, what could we do to lower the emissions? And this is, well, go from fundamental to applied and see if, based on our knowledge of the last 30 years, how we could use that to inform us about the way we could reduce the GHG. There are existing projects, but of course, for future projects, which are still projects, actually. Now, first question, or first observation, reservoirs are not different from natural water masses. Almost all continental aquatic ecosystems, I'm talking about rivers, lakes, are actually produce greenhouse gases. You see CO2 on the left-hand side, and the dotted line, a vertical dotted line, corresponds to the balance with the atmosphere. And everything on the right-hand side are the sources of CO2 for going to the atmosphere. And you can see that almost all the ecosystems which have been quantified, be they lakes or rivers, are actually produce CO2. A few which could be considered as CO2 sink, but most of them are actually sources. For methane, it's even more striking. You see the dotted line is on the left-hand side completely, and clearly all the, we have oversaturation, and which are sources of methane, which is going to the atmosphere. So this histogram is based on about 700 lakes in Canada. You see, it was a pan-Canadian project on the health of our lakes. One on the left-hand side seems to be, but I don't really think so. I think it should be further on the right, well. So this is the situation. Natural systems, aquatic systems, are sources of greenhouse gas. Now, what happens when you transform a landscape, when you build a dam on the river, or where you will submerge territory, the size of which depends on the type of reservoir. It could be, if it is just on the run, well, the inundated surface will be limited. But in Quebec, we are used to having reservoirs, storage reservoirs, which we submerge large surface areas, going from about 10 square kilometers to hundreds of square kilometers, or even over to 1,000 square kilometers, which have been submerged to produce electricity most of the time. Now, in most cases. Now, what I would talk about today is not limited to the reservoirs or to the electricity dams. This includes dams or reservoirs for to do flood control, for irrigation, for drinking water supply, whatever. But the hydropower plant reservoir have some specificities that we'll discuss. What are the main changes which occur when large surface areas are submerged? First of all, you trap a lot of organic matters in the ground, and they will decay. And this, of course, this decay will generate CO2, and or methane, depending on the conditions within this environment. This is the first thing, which is different from the from natural lakes. And another thing, which is quite frequent and normal, I would say, is that when you build a dam or reservoir, we will extend the water retention time in a river, the retention time of a section of a river, let's say the one that occupied the space which has been submerged. Well, we go from a few days, sometimes even a few hours, to now month. And in this additional period of time during which water stays within reservoirs, well, there is more time for the decaying takes place, for the decaying to take place. So it's a change, major change in terms of biogeochemical. I'll come back to that later on. Then we will also create new zones which are likely to become anoxic, and therefore there will be oxygen without oxygen. And even though the surface layers usually remain with oxygen, the ground, the bed of the lake, as of the first millimeters under the surface, well, that has been submerged, we're in anoxic condition, and this will foster the production of methane, which is, and you remember that, which is more radiative power than CO2. And because of the very nature of the reservoir, be it for flood control or irrigations, of course, there will be uh, fluctuations of the river. And in some cases, they can increase more the emissions because we will dry up some parts, we'll submerge again, and so on and so forth. And this will somewhat modulate and in some cases accelerate or increase the emission. Another aspect which, sorry, sorry, sorry. Another thing which is important is to keep in mind, yes, the natural systems do produce greenhouse gases, but the excess of what would have been produced by the pre-existing aquatic system, well, this is a new source of GHG for the atmosphere. So part of the greenhouse gases which come from reservoirs are actually anthropic, and a small part would have taken place even though if we had not created reservoirs. So this is part of the somewhat complication we note in this domain, that is to try to fraction, to define the greenhouse gas between the so-called natural gases and the anthropic gases. But in the landscapes of the landscape, what has changed is it's a sociopolitical aspect in as much as until a recent date in 2009, even if we know since 1993 that reservoirs may be sources of greenhouse gases, all countries of Indonesia, all countries of the United Nations which have signed the major agreements should not, we're not supposed to include greenhouse gas emissions in the national inventory of greenhouse gas that countries have to provide. And since 2019, now it is a mandatory decision was made in 2019. The first mandatory year was 2022, because countries had to adjust and do run the calculations. Well, this is a key factor, another factor, key factor, because we need to try to improve the quantification of those emissions. And the reasons why it took so long to get this obligation, if we want, is because there was no methodology that was approved by all countries, and therefore the GIEC being an organization of the United Nations, it is, it is done through consensus. Since there was no consensus, there was no obligation. Now, consensus have been achieved, and the report you see here, the document, provides tables we call emission factor tables, which are very basic, simple, and which make it possible for any country to assess, in roughly speaking, but to assess at least what is the contribution of the reservoir to their national inventory of greenhouse gases. For example, this is the kind of table you will find between the IPCC report, and if you a reservoir which is under 20 years of age, and we are in the boreal area, for example, well, we multiply this figure, the 27.7, by the surface area of the reservoir occupied in the country, and we get the emission value. And there are several similar tables. So it is something very simple for this to be consensual. Now, of course, it gives us the possibility to all countries to improve this, to try to see what we can do to get a factor or an assessment which is more precise for a given country. And this opens the door to a lot of exercises, modeling exercises, and I will discuss that later on. Now, now we know it exists. What is the scope of the phenomenon at the global scale? Several years ago, about 10 years ago, I was approached by the Association of Hydropower Association in London, based in London, to develop a tool that would make it possible to quantify the greenhouse gas emissions for any reservoir in the world, essentially. And this instrument is online, this tool is online, it is free to use. It's called GRES, and globally it's been harmonized. It is interfaced with the Google Earth Engine, the Earth Engine, Google Earth Engine, which is some kind of a platform to do spatial analysis based on geolocalization. And then we combine this with all the empirical data of greenhouse gases, which had been published until a recent date. And then we were been able to establish a relationship between environmental factors, either general or some specific to one given reservoir. And this is how the tool has been designed. It's based on the literature review combined with global databases on all sorts of assets. And then we made it possible to build, construct statistical models, empirical models, and from which we can forecast, or through simple mathematical equations, the emissions coming from different ways of emission pathways. We'll talk about diffusive emissions at the surface of the what we call the bubbling, and also the degazing, which come downstream from the reservoir as well, and other elements which can be calculated from that tool. It is now well utilized. There are more than 2,000 users from 129 different countries. Of course, it is more used in North America and in some European countries, you see, but still it is quite widely used and adapted. And as I said early on, this model are just empirical functions. You see the equations there. So on we're using different parameters which can easily and directly can be quantified with the instruments without having to do all the calculation. Roughly, if we look at the relations with the graphic illustrations, what we see mainly is that the emissions, the one on the left is the CO2 diffusion, for example, or emissions. Well, emissions will be very high at the beginning, just after the submerge, the flooding, and after with the aging of the reservoir, emission will drop. They will be higher in warmer environment than colder environments, and of course higher in zones where the soil, which has been submerged, was carbon rich, organic carbon rich. And all these are factors, of course, as you see, but the general trend is that temperature is and the age of the reservoir, temperature and age of the reservoir. So this is the interface. You see, you provide information on the landscape, characteristic of the reservoir, and from this you can obtain the image of the expected emissions throughout the service life of the reservoir. And there are other elements which can be calculated to try to see what was the carbon balance of the landscape before the submersion versus what it is today following the flooding. Once we've built the models, constructed the models, which can be used randomly, for example, when an electricity producer wants to assess the emission of the reservoir, well, he will apply this to his or her reservoir. So we combined, actually what we did, we combined this model with all the reservoir of data database I was mentioning early on, which comprises about 6,800 reservoir. That's comprises the largest ones. There are many small ones, but anyway, and we apply this model to all the reservoirs at the scale of at the global scale. And we got a kind of a snapshot in 2020 of an idea of the carbon footprint of the reservoir. And this is what you can see here. Each little dot represents, in fact, the sum of all the reservoir in each of the pixels, you see. And what we can see on the right-hand side of the graph, there are a lot of reservoirs and dams in the Nordic world, Canada and Quebec, and also in European countries. And but emissions are much lower because of the climate, of course, because of the climate which is found in those regions. And here on the right-hand side, you see a graph which shows the distribution, of the greenhouse gases in terms of intensity of emissions, which are the grams of CO2 equivalent per square meter of the surface of the reservoir per year. And we can see we've been able to identify the relative contribution of the various pathways of emission or forms of emission. And for us, one of the main surprise, I'll spare you the details. One of the main the surprise that collectively speaking, we get something like 1 tetagram of CO2 equivalent per year, but about 40% of the emissions take place downstream from the reservoir. They don't even take place at the surface of the reservoir, but downstream from the reservoir, mainly because the reservoirs are often hydroelectrical reservoirs, and water that supplies the turbine is taken from the deep layers where methane usually has accumulated at very high contents. And this methane cannot actually cannot be filtered by the organisms which are in the microorganism we call the methanotrophs, which are trophic organisms, which methane therefore will bypass the this biological filter and ends up in downstream and is emitted downstream from the lake, from the reservoir. Okay, I'm done with that one. And now, if we now look at the total sum, we're not the first ones to, we're not the first to run a global assessment or estimates. At the beginning of the first estimates, there was a major fluctuation in terms of what we considered as being the very surface of a reservoir. One of the first publication by in St. Louis et al. In 2000 quantified the surface of reservoirs over 1.5 million square kilometers. Today, we have a better idea. So as I said, it's more around 350,000 square kilometers, but total emissions, what you can see on the right-hand side, remain very high. And the estimates of the various approaches are somewhat converging, except for the part which takes place downstream from the reservoir. I'll come back to that later on. Now, it is one thing to know the emissions, but what is the impact of such emissions on the climate? Well, the first thing we wanted to look into is the previous slide, which showed the landscape, a snapshot of the greenhouse gas emissions in 2020, according to table. Now, it was not always the case, and we wanted to reconstruct the evolution of the greenhouse gas emissions for the last century. And this is what we've been able to do simply over one century. So by knowing the year at which a dam was built and by combining this with the fact that at the time of construction or the year following the submersion, emissions are very high, but then drop in time. We've been able to redefine the evolution of emissions since the beginning of the last century, that is 1900, basically. So what we did found is that, as you can see here, the peak of the emissions was in 1987. That's the good news. Now, the maximum of the emissions coming from reservoir is behind us since now 25 years, 35 years, sorry, and they're dropping. But those emissions, as you can see, no, they've changed in their total mass, but they've changed in their nature. During the peak of emissions in the 80s, most of the emissions were CO2. But because there was a sharp decrease as the reservoir was aging, the CO2 diffusion emission were dropped as well. And what you can see here on this graph, it shows you that clearly there was a boom of construction in the 40s, 70s, up to the 80s. This is where the major dams were, the major reservoirs were built, and this is why you see the shape of this curve. Now, as I was saying, when you talk about emission, doesn't mean there is an impact on the climate. Well, why do we make this difference? Well, once that a molecule or a mole of a greenhouse gas is in the atmosphere, it will not stay. It will not stay in the atmosphere for the same period of time. Depends on the gas. Methane, which is in itself has a higher radiative effect than CO2, but but it offers an advantage, that is, doesn't stay as methane in the atmosphere for very long. We said the mean retention time is about 12 and a half years. So after 12 and a half years, we will have lost about 63% of the methane emitted. In the case of CO2, it's different. The quantity put in the atmosphere will stay in the atmosphere much longer before being recaptured uh, within the biosphere. Mainly, of course, it's about 1/3 in forest and slightly more in oceans, and there are other reservoirs, biospheric reservoirs, which we will also sink the CO2 or absorb the CO2. Now, it's not the same thing. So when we want to convert emissions and convert that into climatic impact, we have to take that into account, the differences. Now, I'll spare you the equations, but all I want to show you, you see on this graph on the right hand side, just imagine that I build a dam today. Well, I fill a reservoir today, year zero, and once the water has been trapped in the reservoir, the emission will decrease, as you say. But the fact that they decrease does not remove them all. But the peak of the effect of the reservoir, when it comes to methane, for example, will take place about 25 years after the submersion. Even though the emission decrease at year zero, the impact on climate will be at its peak 25 years later. And therefore, what we wanted to do was to combine the emissions we had calculated in time in the history of emissions with what we know about the behavior of each reservoir to get to calculate what was the impact of the reservoirs in time on the climate. So before reading this graph, bear in mind that all the anthropic sources of GHG, methane, and CO2 as well, N2O, and so on and so forth, were created what we call a radiative forcing around radiation forcing about 2.8 watt per square meter in the last 250 years. So even before there was an impact on the atmosphere, today there is a total radiation forcing of between 2.8 to 3 watt per square meter. Now, the gray chart or plot shows you what the reservoirs have done in terms of radiation forcing in time. Now you see in 2020, see, you can see it reaches only roughly 60 milliwatts, 60 milliwatts versus the 2.8 watts of radiation forcing, globally speaking. Well, it's about 1.5% of the total radiation forcing. So the reservoir did not contribute significantly to global warming, but 1.5% is not negligible nevertheless. And when it comes to a mass, it's not far, well, it's around the same figure as the airline industry, the entire airline industry. Now, we can have a closer look and do a separation between. Okay, now let's look at this one here, this slide. We can see that, okay, we see the radiation forcing associated with CO2 and the one associated with CH4. CO2, you see, what we see is that the maximum, which is around 2010, reservoirs did contribute to only 1.6006% of the radiation forcing of all anthropic CO2 sources. So it's fairly limited. For methane, situation is quite different. At the peak, which was again around 2010, reservoirs, based on our calculations, well, amounted to 6% of all anthropic methane emission. So it was not negligible at all. Currently, it is dropping, partly because methane emissions from the reservoirs drop, but it drops because other methane emissions, anthropic methane emission, which have nothing to do with reservoirs, increase. So the relative contribution of the reservoirs drops. Relatively speaking, what you see on the right-hand side of 2020, the scopes corresponds to the various scenarios of what will happen concerning the emissions of other sources, based on scenarios which are more or less optimistic. Now, let's go now into the last section, which will be brief, on what can we do to reduce those GHG emissions. Well, the first point when I was facing these questions is I was doing research work on a hydroelectric reservoir in the Borneo Island, the tropical reservoir, and we did quantify the emission pathways, bubbling, surface emissions, what happens downstream from the reservoir, and we realized, in fact, that most of the emissions happen to be, well, that is the percentages you see. Well, you see 54 plus 10 plus 18 plus 18. Well, we get to the point that most of the emissions of the reservoirs take place downstream from the reservoir, and there were very reasonable values at the surface of the reservoir itself. So what was more striking actually for us is the fundamental part of the methane. Methane is produced mainly in sediments, and when you are in anoxic zone, the methane will migrate closer to the surface, and there could be, as I said early on, there could be a filter or biological filter. But to produce hydroelectricity, of course, you have to go get water somewhere in the water column. And in the case of the methane A, you see on what we call Batangai, you see vertical profile of methane concentration. So you see it's not very high at the surface. You see 0 is surface, 35 is the depth, and well, zones are less pronounced with lower concentration than at the end. And this is a logarithmic scale. That is, between each unit, there is a factor of 10. If we take water here, and let's say 22 meters, and if you take water here at 10 meters, well, there is a factor of at least 100 times for the concentration. So factor, that will have an impact on the GHA footprint of the reservoir. And we've made calculation which showed that if water entry had been positioned a couple of meters higher, I talk about 4 or 5 meters only, higher than what was done in this reservoir about 30 years ago. Well, we would have reduced the greenhouse gas footprint by 90%, which is huge. And of course, we cannot deconstruct and rebuild. We can, raise and rebuild a new reservoir which has already been constructed. But it could be possible to play with the water level, because where there is a minimum of concentration is often where the temperature and oxygen will change rapidly. And by changing the water level, we could change the quality of water, which is and where which is taken and which will produce greenhouse gas downstream. So we could work on this, and this could be, even before modularized, to before we build the reservoir, to see which will be the optimal location to have the water, chute for the turbines, so as to reduce the greenhouse gas footprint. Now, just to impress you, to show you how smart we are. But anyway, we've developed a digital model, which we do. Uh, we couple physics and geochemistry of systems to see, okay, where will the transition between hot and warm, cold, and where there will be oxygen and where there will be no oxygen, so that we'll be able to quantify the location or identify the location which would be most likely to minimize. And I want to show you, do a little animation. We run the model, and again, you see here methane concentration, a methane profile from the surface to 25 meters, and I will run it for 1 year. So we'll see it for, you see the change every day, you see how it changes. And so let's stop it now. You can see how within the about 10 meters, there could be very different concentration. This is about 17 in depth, and this is about 1.1, 0.1 at 5 meters. So, of course, there are constraints associated with the flexibility we wish to give to a hydroelectrical dam to produce more or less electricity, but we could well imagine, well, build or install the water chute, the water chute inlet at the certain time of the year, so that the water that is being turbined is very poor in greenhouse gases and not rich, as it is often the case, because as the chute inlets. Okay, I'll look at it. So this was a brief example to show you, to illustrate how, with the knowledge we have today, with the IT tools, we could, even when just when planning the dam or the reservoir, we could foresee or estimate the biogeochemical functioning of the system to reduce its greenhouse gas footprint. I think I'm done with my time. I will stop now, and I'm very happy to answer your questions. Just by way of conclusion, dams can be high sources of entropic greenhouse gas, depending on the environment. The emission peaks that we've seen are behind us, but collectively speaking, they're still contributed to the entropic emission, especially for methane. I'll stop now. Thank you, and I'm open to any questions. Thank you. Is there off-the-cuff rule to assess the depth at which methane content increase in percentage of the total depth? Very good question. I don't know. I don't know if this the rule. Well, we, depending on the location, on the exposure that the dam will have in exposed to wind, for example, we can determine at which depth we'll find the thermocline, where basically temperature will change rapidly, and it is often a few meters. When I say a few meters, it could be 1, 2, 3 meters below the thermocline that we will find the minimum concentration of ethane. Topically speaking, a dam, let's say 80 square kilometers, well, the thermocline and will be about 10 meters. And typically we could install the inlet at 13 meters. Well, if it is a smaller reservoir, it would be higher in the water column. That is the inlet for the chute. More, eh, well, now we have tools, modeling tools, which would make it possible to quantify that uh, easily.
Alors, je prends un peu d'ordre. Merci pour la réponse. Je prends un peu l'ordre des questions. Il y a Colline qui
Colin
demande
ask us,
comment
okay,
ça se passe par rapport à ce que tu proposais de potentiellement
can you talk more about
réduire
having
les
water
niveaux d'eau pour
intakes
pouvoir réduire
up
les impacts
higher? How
des
does that
changements
work with increasing
environnementaux
sediment buildup in reservoirs?
si par exemple on a de
For
l'accumulation de
example, if
sédiments
there is
qui
accumulation of
vont
sediments,
aussi au cours du temps dans
which
le
increase in
réservoir.
time in the reservoir. Another good question. Well, there are reservoirs which, from the design, from the very design, include several water intakes, inlets, which can be used at different times. The chute inlets, which could be which we can draw water from different depths at different times. This is very useful, not for a reservoir which had a fixed water inlet. It's almost impossible, except if we were to build a wall be in front of the dam that would force water. Uh, that would have to come higher in the water column. Those would be very complicated to do. I'm not an civil engineering engineer. I'm not a dam construction engineer, but it would be very difficult, certainly. Now, I believe that historically speaking, in terms of reservoir, we never asked ourselves the question because no idea about their significance in terms of greenhouse gases, and we put it as low as possible to give ourselves the maximum flexibility in the water level. But now, if we assign a dollar to the carbon emitted, well, of course, we could possibly toy with the water level. It will be more economical to drop the water level, even if we produce less electricity, if we reduce significantly the greenhouse gas footprint.
De l'abaissement des niveaux d'eau pour
Talking about the water levels,
les impacts. Donc,
to mitigate the
merci
impacts, we talk
pour
about
le
that. So
commentaire
now,
de Monsieur Michel
based on
Lafort
the
qui
comment
dit
of
ça
Michel
pourrait
Lafort, who
aider
works on the
à limiter
restoration
les niveaux
or
d'eau et qui
of
propose
water
des solutions pour
masses, and he talked about the solution considered to toy on the profile of temperature and dissolved oxygen to modify the concentration in CH4. So just okay. Michel Lafort gives his email address, by the way.
Et si je reprends
And now,
aussi les autres questions,
now as to the other questions,
il ne faudrait pas retirer la forêt
shouldn't we? Is it necessary to remove forest before the submersion to avoid the greenhouse gas emissions? C'est pas la clé. It's not the silver bullet to reduce emissions because, well, of course, it may change in terms between tropical countries and Nordic countries. But for example, for us, we can dive in reservoirs which were submerged, which were filled 30 years ago, and the forests are intact. There is no degradation of the biomass itself or the of the trees or large branches, so that do not contribute to the significantly to the GHG emissions, and even in tropical environment, in oxygen-free environments, even after 30 years, the wood has not changed much. It hasn't lost much of its carbon. Actually, a project would like to go and cut the trees because wood uh, is in good condition. So,
Il y a une remarque
a comment from
question,
a
remarque
question
intéressante de Frédéric qui
from
demande
Frederick,
est-ce
who
que
wants
par
to know
rapport
now,
à toute cette analyse que tu as montrée sur
based on
l'émission,
the analysis you've shown on the
électricité par les barrages,
greenhouse gas
avec
emission
cette énorme
from dams,
énergie
because of the
produite
huge
par
quantity of
hydroélectricité,
energy produced by hydroelectricity,
finalement c'est pas positif.
well, is it not positive in a way? I don't know if I.
L'analyse du cycle de vie d'un barrage n'est pas
Does
positive pour
the life
cause de
cycle
l'énergie
analysis,
produite par
the
l'hydroélectricité.
analysis of a life cycle of a dam is positive? Well, we did publish a paper about 3 years ago where we worked that on with the dam, analyzing the life cycle on the stock of dams in Quebec, and even when we look at it at the level of the entire life cycle of the dam, emissions are associated with the dam, and that comprises construction, that includes all accumulated emissions over a service life, which is about 100 years. Well, it is still very highly advantageous compared to any other domain of electricity production or any other electricity production systems. I can send you a copy of this article.
Il y a une question également, est-ce que dans ce que tu as montré,
In
vous
what you've
avez
shown,
distingué aussi
did you make a
les réservoirs
difference
de l'eau
between the on the run barrage? Yes. On the run dams. Well, sorry, the reservoir we modelize are storage reservoirs, but they are on the run reservoirs, which we studied. And of course, there are less reservoirs have been studied because the modeling initially, which are called statistic empirical, well, these are database. This is data based on what has been measured, and we got a lot more measures in measurements in storage reservoir than from on the run reservoir. So it's still a sort of a blurry point. But anyway, still, there are examples in Europe, at least, where on the run reservoirs, so with no submersion, which are high emitters, because reservoir will tend, especially in very large population area, will increase silting, and this silting will increase the production of methane, and there will be methane hotspots.
Toujours sur les petits réservoirs,
Still on small
Teresa
reservoir,
qui demande si tu as
Teresa
étudié un petit peu
wants to
les
know if
effets
you got
serrés
an idea
sur
of
les
the
petits réservoirs.
emission potential of small reservoirs. Depends what you mean by small, actually. One of my students who, well, last summer assessed the greenhouse gas emissions from the very small reservoir. When we talk about small reservoir, we talk about those are lakes who put at the dam at the end to increase water level and have a larger surface to get, it's like kind of national sport. You have your little cabin, next to the lake. But anyway, and most of the reservoirs are quite old already, so we don't have many indications, but we consider that it won't be that big, not that significant as a total footprint of greenhouse gas from small reservoir, still to be quantified nevertheless. Marine would like to know, would there be operation mode that could be installed during the first year of the reservoir, operational life for reservoir, so that maximum of methane would be diffused rather than degassed in time?
Bon point.
That's a good question.
Ben, à vue de nez, l'idée
Well,
serait
the idea would be
dans
to
les premières années
that the first year
de garder le niveau plus
to
bas
keep the level
jusqu'à temps qu'on
lower until
sorte le taux d'émission
the
de ces gaz à effet de serre
production
de l'atmosphère.
rate of the greenhouse
Et une
gas
fois qu'on a
drops, and
vraiment
then
monté le niveau de l'eau,
increase the
on
water
peut
level
l'exploiter
to
d'une
run
certaine
it
façon pour
to
l'électricité.
produce electricity.
Peut-être
While
en balançant, si on veut, ou en
while
réduisant le taux d'émission de gaz à effet de
reducing
serre
the
de l'atmosphère.
greenhouse gases. It's good,
Je
great
dirais
point.
que
Great point. I never thought about that. Yeah, good, good.
Est-ce que moi je peux poser une question?
Can I ask a question, Sio?
Non, pour rebondir sur le méthane, tu montres bien
Back
qu'en
to
fait,
methane,
avec le
which
temps,
shows that
il y
in
a une
time,
diminution des émissions
there
de
is a
gaz à effet de serre
reduction of total
qui est
emissions
considérée
because
qui va
it
avec
is mainly
les
CO2 which
émissions
drives the
par
peak of
exemple de
emissions,
carbone.
especially in
Et
the
il y a
80s.
un
But
déclin du méthane.
there is an increase of
Et
methane,
du coup,
and
pourquoi il y a eu
therefore,
cette augmentation
where does it
depuis
come
les
from,
années
this
passées?
methane
Est-ce que
increase? Because we
ils
could
recyclent
consider that
pour
large part of the organic matters
reminéraliser
have
petit à
been
petit
mineralized in the
les
first year
réservoirs? Donc
of
pourquoi
the
il y a cette
reservoir.
conséquence du
So
méthane
why
aussi?
don't we see a decrease of methane?
C'est-à-dire que
Well, in
le
fact,
méthane, il y a une
methane, well, there is a
décrease de
decrease in methane,
l'efficience
but this
émettrice
decrease is
due
slower
à la
than that of
consommation
CO2. So therefore, we have a
d'énergie
feeling that the relative contribution
importante. Mais il y a
increases.
aussi,
But of course, there is as well.
je pense que quand on est rendu surtout en
When we in methanogenesis, when we
qu'on
produce
consomme
methane through decomposition of wood,
donc
it is much
la
slower,
contribution du
though
méthane
the methane contribution
à
increases
travers le temps
in
va
time,
durer beaucoup plus
but
longtemps
will last longer
parce que en
because
termes de
in
masse
terms of
moléculaire, le méthane
methane mole
est beaucoup plus
versus CO2 mole, it's much
rapide,
slower. So the degradation,
est quand même beaucoup plus lent
it's
sur le
much
processus
slower
surtout
when it is done
décomposition.
by methanogenesis.
Il y a juste Monsieur Lafort qui précise aussi que
Monsieur
il y a
Lafort
des
specified that there is the importance of the
niveaux sensibles
presence
de la profondeur
of
qui peut potentiellement
the
contribuer.
Ouais,
trophic level,
on travaille
the
spécifiquement
hypolimnic
à voir
anoxia.
si
And this year, summer, we worked on a reservoir
50 mètres de profondeur
which
sur
about
toute l'année,
50,
euh,
60 meters in depth,
tout
and
l'été,
all year
avec des
round,
dribs de glace,
every summer,
il y avait
throughout the summer,
plein d'oxygène
gas-free
dans le
period, there was a lot of
réservoir. Là,
oxygen in
on
the reservoir.
voit
Well, we
quasiment
can
aucune
see
accumulation de
almost
méthane
no accumulation of methane.
dans le fond. Donc, dans ce cas-là,
So in this
on
specific case, but
commence
again, this is a Nordic environment,
très
so methane
sensible
production is highly
aux
sensitive
températures
to temperature.
chaudes,
And,
que ce soit l'hiver ou l'été.
winter or
Le
summer
fond
for
du
us,
réservoir,
the bottom of
du lac
the
est
bed of the reservoir or the lake is always the same temperature.
à
It's
quelques
always
degrés.
at
Donc,
4 degrees,
les sédiments
you know,
de nos lacs
sediments in our lakes, Nordic
sont
lakes,
vraiment au
are
réfrigérateur.
always in the freeze,
C'est sûr
in
qu'il
the
y a beaucoup de
fridge.
méthane qui
Of
va
course, not much methane will
de
precipitate,
l'hydrogène,
and there is a lot of oxygen.
alors
So,
que le méthane
therefore,
comme l'hydrogène
methane
ne serait jamais là.
will never, almost never accumulate in these zones.